Let's now talk about the subject of linearization, which is needed because we need to be able to, if you like, calculate linear approximations to our system at certain points. And this follows very much on also from what you do from control engineering, except now what we're going to do is we're going to calculate linear approximations known as the Jacobian of the robotic system. And we'll do that because we'll want to, in a bit, calculate relationships between small changes in angle at the joints and how they correspondingly change the position at the endpoint, and velocity relationships also are played out with using the Jacobian approximations. And finally, of course, we're going to need to calculate relationships between force and torque. So what's the force at the endpoint given the torque at the actual axis? So often we're going to have equations, differential equations of the form x dot is some function of x, where x is a vector, and the function of x is going to be built up of lots of different parts, basically. It could be a set of equations, indeed. We can linearize a nonlinear system using a Taylor expansion and then basically throw away high-order terms. And we effectively end up doing calculating a Jacobian matrix, which can linearly approximate things at a local location. And in control engineering, for example, we would calculate the Jacobian matrix at equilibrium points. Now, we don't need to do it at equilibrium points with kinematic models. What we want to do is we want to be able to calculate it at a given configuration, so we can approximate what's going on at that particular configuration over small changes. And the matrix is of this form, right? If we've got a Jacobian matrix, basically the different rows corresponds to different functions, and these functions are functional expressions. Basically, you get one for each row, and we find the overall partial derivatives with respect to all the variables that actually change within the system. So, first function is differentiated partially with respect to x1, x2, and so on, and so on for all the different functions we have. The effect of actually calculating the Jacobian is to, like I said, it's to calculate a linear approximation, and we can then evaluate that at a given point. So, for example, if we wanted to linearly approximate a surface of this sort of parabola in 3 dimensions, what this would result in is at any particular point on the surface, we're saying we can approximate the gradient, in this case by a plane. And depending on the direction you go in, you'll get, obviously, you're going to get different values. So here's the Jacobian matrix, and basically the term delta F1, delta X J basically relates to the derivative of the ith component in terms of the variable xj, right? It becomes much clearer when we start actually doing examples of this. If we had a 2-variable function, for example, when we do partial derivatives, don't forget everything apart from the thing we're actually differentiating with respect to is considered a constant. So if we do the derivative delta z delta x, in this case, y would be considered to be a constant. And that's how we basically specify it as being partial derivatives. We use these curly brackets, these curly d's, rather than the straight ones. Again, this is then an example of doing it with respect to y. Now let's think about a couple of results that we need to work out, because we'll need them a little bit later on. So if we've got sine theta 1 plus theta 2 equals y, what is the first derivative? Well, what's the derivative of this with respect to theta 1? So we can write that down as we're going to take the derivative dd theta 1 of this expression sine theta 1 plus theta 2. Now what we have to do in that case, unless you know the answer straight away, we have to do basically the chain rule, right? So we're going to say that let's consider theta 1 plus theta 2 equals u and y equals sine u. Therefore, we can just do the individual derivatives. Delta u d theta 1 is going to be 1, because theta 2 is a constant, so it disappears, and theta 1 goes to 1. Y equals sine u, so dy du is going to be cos u. And the chain rule then, we have to multiply those two parts together in order to get the overall derivative. So we multiply cos u dot 1, which equals basically cos theta 1 plus theta 2. Thus, when we take the derivative of sine theta 1 plus theta 2, it equals cos theta 1 plus theta 2. If we do cos theta 1 plus theta 2, we have to do exactly the same approach in order to do the derivative, let's say with respect to theta 1. Again, we use the chain rule in order to split it up into two functions, the addition part and the cosine part. So u equals theta 1 plus theta 2, y equals cos u. Therefore, again, du d theta 1 equals 1 because theta 2 disappears. And of course, dy du, in this case, cos theta goes to minus sine theta, so we end up with a minus sine u. And we substitute back in to the chain rule, put all the values in, and we end up with our derivative now becomes minus sine theta 1 plus theta 2. So it'll become apparent why we need that a little bit later on, but we need to be able to differentiate things like sine and cosines and sine something plus something, because they're the form that you get in our forward kinematic equations, right? So we have these theta 1 plus theta 2. You get that, certainly you get for a two-joint planar arm. So the differential Jacobian, this is this thing that we're using to linearize around a certain point, can be used to calculate what happens with little tiny deviations in the configuration around that point. So what we can effectively say is we can use, normally we use form kinematics to determine the position and orientation of the end, and that's fine. And we can use inverse kinematics to do the other way round, right? So it's a forward kinematics, we go from joint space to task space, and direct inverses would give us the ability to do inverse kinematics. So we go from task space back to joint space. But interestingly, well, it's easy to do the forward transformation, right? Because we can put all the values into our homogeneous transformation, calculate the position and orientation of the endpoint. So forward kinematics maps the joint parameters to the end parameters. We've got an expression with lengths of the links, and we've got thetas in there as well for all the let's say all the joints. We can do that. So that's easy to do. So end effector position, therefore, is going to be a function of the joint parameters. Now, when we're talking about instantaneous differential effects, we're talking about small deviations in joint parameters, and how are they going to affect end effect position. So what we're going to say is, imagine now we perturb the joint angle by a delta q. So q is the angle vector, say, and delta q's are just a little tiny deviation from that. This is going to lead to a small change in the end effector position. So if x is the end effector position, that's going to go to x plus delta x. So the idea is we're going to, in this scenario, we're thinking about making a little change in the parameters of the robot joints, say, and we expect to get a small deviation in the position at the end point from that. So given we've got this relation, we can also write this down in the functional form now. So we're saying that x plus delta x, so x plus the little bit of change that we're going to get, is some function of the angle plus a little bit more angle. And then we expand this up then using a Taylor expansion. X plus delta x is going to be the function of x plus the first derivative, right, times a little change in x and higher order terms. So basically what we can say is that the delta x is approximately equal to this differential of the function at a particular q value multiplied by a little q value, right? And we're going to see that this is actually going to be then given by the Jacobian of this system multiplied by a little change in the angle. So, and that will give us a little change in the end position. So JOX is the Jacobian matrix. So we can use the Jacobian to map between little changes in joint space to little changes in Cartesian space. That's the idea. So a little change in joint space multiplied by the Jacobian at that particular configuration, and that's very important because we're only allowed to do a little bit around where we're evaluating the Jacobian. That gives us the little tiny change that we get in an X. And of course, this is what the Jacobian is going to look like. In this case, if Q is now the angle, then obviously for each element in the position vector here, we have a row. We differentiate that with respect to all of the parameters in order to get this Jacobian matrix. So we can use this then to map between joint angle and corresponding small changes in end effector position, but we can also use it to map between time derivatives as well. We can also say x dot, which is basically going to be some velocity term, is the Jacobian of the system multiplied by the angular velocity term of the joints.